We have now to speak to you, Toby Scott, who is a Year 10 student at the school, and we'll be talking to you about not a line follower, but a maze solver and Python. So, without further ado, if you carry on when ready, sir.
Hello everyone, I'm Toby, and I'll be doing maze solving in Python. I just want to give a little bit of history first. So I think I started around in year 8 doing this sort of stuff, and I started with wall following, and then I came to the Hazelmere 2022 competition and did that, and then I decided with Mr. Fisher and my friend Malcolm we'd start doing maze solving, and so this is just how our approach is now, and then Mr. Fisher will talk about the past and what we plan to do in the future and the problems we've had. So we use the standard UKMARSBot with a Raspberry Pi Pico W, so that allows for Wi-Fi and Bluetooth capability. We have a separate serial connector on the side, so that allows for us to use a 5-volt Bluetooth module or a TV remote receiver. And we have a 4-switch module connected to digital inputs, as the Pico only has 3 analog inputs which we're using for the sensors. And we have buffers attached to the side to stop our sensors getting too close to the walls of the maze, because when they get too close it can change the values. So you can see here, this is where we plug in our Bluetooth module or TV remote receiver. So I've got a code breakdown. So we have a program called Sequencer, which is our main code, and that controls all the other codes. We have a movement code, which is in charge of all the movement of the robot. And we have the solver, and all the programs talk to each other by passing instructions through functions. Then we have UKMARS New, which allows us to access the inputs and outputs of the bot in an easy way. And we have TVRlib, which allows us to use the 5-volt connector. So Sequencer. Sequencer is the control program, so it controls all the other programs. It can respond to human inputs, so button presses and a front sensor start. And different parts of the Sequencer program is broken down into functions, so we can easily break down each part. So if we're using the solver has its own function, the part before starting the robot has its own function. And determine what functions to call, we use our digital switches. So switch 1 determines if we're in wall follower or maze solver mode. Switch 2 determines frequencies for Bluetooth or remote functionality. And switch 3 decides if we're using the solver or the human to control the robot. And switch 4 is currently unused. So some of the functions we have is remote, and that allows functionality between the Pico and the serial connector. We have button press, which monitors for a button press, and depending on the length of the button press, can return a string either L for long or S for short. And log, and it writes what walls are present and the commands sent to the robot by the remote or solver, and it also sends that data out via Bluetooth to a Bluetooth terminal or a maze mapping software. And display is the code is before we start the robot, so that waits for a front sensor to hand in front, and whilst waiting it outputs the analog values from the robot. So the main functions is maze, which is when the solver is in control. So we read the walls using m.walls to determine what walls are present. We send the wall values to the solver code and waits for a command to be sent back. So after a response, we log the walls and the response, and then we send the command to the movement code using m.move. Because we have different phases of solving, which will be explained later, when we have going from phase 2 to phase 3, we have a list of commands to get to the centre of the maze, so we don't have to keep consulting the solver for commands. And then also during that list we could have multiple forwards which are combined into one long forward, so the plus, which is used to represent a forward, is followed by a number. So that can be executed with one forward at a higher speed. Then human control gets a command from the Bluetooth module or TV remote, and then reads the rules for m.rules for the log, then calls the log function, then executes the command using m.move. This function is used for debugging and testing movement functions. So if we want to know if our robot is turning left enough, we can use human control. And any function with m. is located in the movement program, which will now be explained. So this is code in charge of the movement of the robot. It uses encoders and interrupts to work out distance travelled, and it compares the encoder values against preset variables located at the top of the code for easy access to ensure the robot goes the correct distance. And a variable called inteb controls whether interrupts are enabled as in writing to the log, and we receive an interrupt at the same time that causes our robot to crash. So forward function is used for going forward one or multiple cells. It starts by determining what walls are present for steering and correction. It then enters a while loop that will break under two conditions. If the robot is too close to the front wall, and this is found by comparing the front sensor to the threshold variable called f-stop, or if the robot has moved the correct distance. And then steering works by comparing the left or right sensor value to the target value, which was determined earlier. So it uses the wall present to determine what values to steer on. So if the right wall is present, it compares the right sensor value against our right wall target. When both left and right walls are present, we use both and find the average. The product or the error is then multiplied by our mult and added or subtracted to the motor speeds. Acceleration is used when going more than one cell at a time, so this is during the last phase. It starts at a lower speed and gradually increases until it reaches the desired speed. And when reaching the end of the forward distance, it slows down for a better stop. Because when we're going from a quite high speed to a complete stop, there can be quite a lot of skidding. And correction works by when a wall disappears, it will know the correct distance, because if the wall was there before starting but then disappears halfway through, it knows where it will be and then the rest of the distance to go. Currently this isn't working because we're having a couple of teething issues, so it won't be enabled on Sunday. And the benefit of this, it gives an exact stop when travelling large distances, and it also has hysteresis. So our turning functions have three parts to it. It has the forward before the turn. It then has the turn, which works by having only one motor running, so it pivots off the inside motor, and has a forward after the turn. And the distances for all of that is determined at the top of the code for easy access. And they're for variables for each the left and right turn. U-turn, it reads the walls before starting to determine if there's a front wall. It does the 180 spin, and if there was a front wall before spinning, it calls go back, and then goes forward one cell unless at the end of phase 2. If there wasn't a wall in front before spinning, the robot doesn't call go back and just goes forward. So go back is our function for backing into the wall until it can't move any further back, detected using the wheel encoders. It does this so the robot starts right at the back of the cell and level. And then forward simple is a more simplified version of the forward routine. It has no hysteresis, correction or acceleration. It does have steering to correct if the robot is too close or far from the wall when in the turning or U-turn functions. And move has a movement instruction passed to it as an argument, and uses if statements to determine what movement function to call based on the argument passed. And in phase 3, I've mentioned that. And then calibration, it sets new threshold values for both the left, right, front walls and the f-stop value. And it indicates what thresholds are being set using onboard LEDs. It writes the threshold values to a Python file, so they're imported at the start. and this provides an easy way of getting new threshold values for a new maze, as different mazes have different reflection values. And walls reads the walls. It determines what walls are present by comparing analog wall values to the present thresholds when calibration, and then if the wall is more than the threshold, the wall is present. And variables L, F and R are set to 1 if the wall is present and 0 if it isn't. So this is the solver now. My friend Malcolm would have been presenting this part, but unfortunately he can't make it today because he was ill, so I may need to look at my notes for this part. So representing the maze is done by 1 byte. The first 4 bytes are for the walls of the cell, so north, east, south and west. And then you have a done flag, which is used to make sure instructions are not overwritten when solving. And the 6th bit is used for working out if the robot has actually visited the cell. And the last 2 bits are used for movement instructions. That's because we use a string-based solver method. So we have the solving algorithm, so we use a string-based algorithm. So it records the movement would be taken if it was in a specific cell. So it has the target cell, which is up there. So if the robot was, for example, here, it would be going this way. And this is quicker and takes up less memory, theoretically only taking up 256 bytes, although the rest of the solver object brings the solver file to around 2 kilobytes, out of the 264 kilobytes the Pico has. But we used to use a flood fill method, which has it was more slow and required a 3rd times more memory. And each cell has a number of how many cells are in between the target cell and it. So if it was here, it has 4 cells in between it and the target cell. Our solver is a class-based, and that's an advantage of MicroPython has over a lot of other languages. And this allows us to group all the solving functions and variables, making it more easier to read. So for example, we have .solve, .wn, and we've got some variables like .direction and .pos, and they're all in the solver class. So phases. So the solver has 3 solving phases. It has the first phase, so that finds the route to the target cell, or end cell, and then it returns to the start cell, maybe by a new and faster route. So that makes sure it maximises the amount of space in the maze the robot visits. Then we have phase 3, or known as the final solve, which returns by the fastest possible route, and that uses a pre-compiled list of commands. But as you see here, the robot is using a path that we haven't actually looked at, so for all we know, there could be a wall blocking it. So we've recently changed the solver to block off any cells that haven't been visited, so then it routes via cells we know where there are walls of. So our other code, so the libraries we mentioned earlier, we have TVRlib, which is our TV remote library, which is a class base for the use of UART and receives and sends data. So it consists of 2 functions, get, and this receives 1 byte from the serial connection, which is represented as a movement command, and that can be received via a TV remote or Bluetooth. And we have send for sending out a string, so that's normally the wall values and the command via Bluetooth to our Android app or to a Bluetooth terminal. We then have UKMARS New, which was developed by Mr. Fisher, and this provides an easy way of accessing all the inputs and outputs of the robot. So this has functions for each part. So you can access the switch values, LEDs, motors, wall sensors and inputs from the encoders all through UKMARS. It does this for the new and old Raspberry Pi Pico piggyback board, as before we used the Stephen Pithouse design, we had our own design. I now welcome up Mr. Fisher to present the past, the future and, what's the last part? The problems.
I'll do this and then I'll talk about how we developed it later. The robot, as indicated, is not a standard UKMARS robot. It is actually quite an old UKMARS robot from over 2 years ago. It was a very early start, and we didn't change anything with the new sensors. Because we're using the Pi Pico, we need a piggyback board. And we're not using the standard serial port side. We've got our own serial connection. A, it makes it easier to disconnect and connect, and B, it actually gives us 5 volts, which is necessary for some of the adapters we're using. Because the Pico only has 3 ADCs, analog converters, we can't use the normal four codes, 4 switches. So we put a digital connection in through to the additional digital inputs that the Pico has that the Arduino doesn't. And in a school environment, it's essential to have the switches to try different combinations without having to go back to the computer and re-download every time. The program, as I said, well, I'll drag a bit past it now. It's heavily influenced by the PIC1 maze solver, which had 2 separate processors, one for movement and control of the robot, one for solving. And this is exactly what we're mirroring here in our subdivision of the code, and also the subdivision of the team. It wasn't emphasized, but Malcolm, very sophisticated, very a good programmer. He is really good, and he's acknowledged across the country apparently. Has done the maze solver, and he's progressed it in a variety of ways to display what it's doing, to run it with a number of different mazes without even having a robot. Toby has done the overall sequencer and movement side, and also, I should say, he has done the whole of that presentation.
Malcolm has done parts, but...
Malcolm's done parts as well, okay. Right, what went wrong? A significant thing that went wrong was that it would enter a cell, and then it completely ignore that cell and go immediately onto the code for the next bit of cell. And what was happening was that in the movement, it was resetting the distance counter, but there was a collision between the interrupt software and the main code, and we didn't realize that you actually got to either stop the motors or stop the interrupts, because the 2 bits of software were both trying to write to the same location. We tried disabling interrupts. However, this collided with the log file functionality in Python and caused the whole program to crash. So we ended up with a flag saying whether to write or whether not to write in interrupt software. That was probably the most significant problem we had. I have got a problem at the moment with the distance correction, which is something which we also solved. We also inherited from the PIC1, which is set your cell distance slightly longer than reality and correct it each time from the disappearance or the arrival of a new wall boundary. That is causing us still some problems. The future. Diagonals. We recognise that we're going to need different sensors, or at least more sensors pointing up the middle to get us up the diagonal, but I think we've got enough coding ability to do this, and this is what we're aiming for next year, but we're not doing it this year. But
I just want to go through some credits and thank yous. So I want to credit myself. I'm one of your hosts and developer of the sequencer and movement codes. I'd like to thank my friend Malcolm Loggie. He's responsible for the solver in TVR lib file, and I'm able to make it today because of illness. Thank you to Mr. Fisher for developing the UKMARS new.py and a massive help with robot development. Mr. Clapson, one of our STEM ambassadors and volunteer at St Albans Robotics Club, and Mr. Robinson, organiser of the club, and also I'd like to thank with his extreme patience with me and Malcolm. And thank you to you for listening. And are there any questions? Yep.
You mentioned calibration. Do you have like a procedure for that, or do you mean with manual values?
So the robot all does it itself. So I'll just get some pictures up.
Not entirely true. And when you switch it on, it is now waiting for a start signal. If you do a short start signal, it will start running.
You need to hand it in front longer. I'll show you.
Okay.
So a short press will continue on, but if I do a long press, you'll enter calibration mode. So as you can see, we've got onboard LEDs here, here, and here, and here. So depending on what threshold value is being set by the robot, depends on which LEDs it turn on. So if it's doing the left wall threshold, it will turn on the left LED, and so on. And for the S-stop, we use the Pico onboard LED. And so then it does it all, sets the threshold all by itself, and then logs it to a Python file.
The calibration is literally of the sensor values for all present, all absent, and the long distance front stop to see if there's a wall there, or long distance front sensor value for wall presence. And then there's a shorter one which we also calibrate for, which is the emergency stop if you've overrun.
So do you put the robot into a position in the maze?
Yes.
And then tell it to calibrate?
Yeah,
We
so
have a video of it somewhere, but
you put a position, you put it in the maze, and then once you've got it in a position you want, you press the button, it will take the reading, and then it moves on to the next one, and so on. And then it cycles through all of them, it logs them, and then it just goes back to, so if I just...
but they're then written to a file, so you don't have to calibrate.
And then it just
for
goes
every
back.
different maze.
It goes back to its normal state and ready to start on the new run. Yep.
I'd like to find out a bit more about the string-based solver that you mentioned. Probably not now, but we perhaps have a little chat later about
It's
that.
probably Mr. Fisher
Yeah.
would be best to talk
We're
about the
talking about
string-based solver.
list-based solving as opposed to complete flood filling.
Right.
And obviously, if you're going from a list, you'll
I think-
process fewer cells.
Ah, right, okay.
But I just double check something.
But
Well, the notes
the
here.
big one that we looked at first is list-based. But a lot of other code that we've seen is actually flood. You basically look at every single cell, which is too much.
What my friend's put here says we use two lists of cells which are swapped back and forth to solve the maze, so we don't have to iterate through the lists loads of times. But I'm not very confident on the solver part, so.
I think
Okay.
that's a method that, if not unique, is certainly new to me, and I think it would be very useful if perhaps at one of the monthly club meetings or something, when your friend is back in better health, that we could perhaps very usefully get
Okay.
some more information about it.
Malcolm has actually measured times for solving.
But some of them are so short that it doesn't actually register as a thing. So because like sometimes we'll just get 0 milliseconds because it takes so little time to actually solve. So
That's just showing off.
it does take longer on a bigger maze though, because we've only got an 8x8 maze upstairs in our computing room, but obviously it's a 16x16 at a competition.
But
So yeah.
what this emphasises is that the project can be split into watertight compartments. Because Malcolm's not here, we can't answer this question because we haven't had anything to do with it. And likewise, he hasn't had that much to do with movement.
Yeah. Classified information.
Yeah, thank you.
Are we done?
I'd like to know how the Bluetooth works, like in a separate conversation as well.
We use the standard HC05 module.
Yeah.
And it runs at 9.6 kilobits for the serial.
a bit more interested in a lot more like lower level detail of like what pins you're using, what the code looks like, what apps
We're
you're using.
using the standard
I
UART
can
pins.
maybe get the codes up.
I'm sorry.
You can
Just
use-
serial input output. There's two on the Pico. One which is the USB connection,
Yeah.
and the other is an additional one. It's the UART 1 as opposed to UART 0. And we use one for Bluetooth and one for the REPL talking to Sony.
Ah, okay.
So
That might be the critical answer I was after. It's all going through phone.
okay. But please come and ask questions the rest of the day if you want to see more detail.
So that's our class. So we've got the remote class, and then we've got init, get, send, and print. This does the same thing as send, so they both do the same thing. So it's just all contained in here.
Okay. Well, thank you very much. That was very impressive.